Okay, we're going to continue on here, chapter 16. We're almost done with it. A couple more things to talk about. But we talked about a lot the other day, and we talked about obviously our KW, which is again our H plus concentration, and our OH minus concentration equals 1 times 10 to the minus 14. Again, we could use this as we've done to calculate either the H plus concentration or the OH minus concentration, depending if you're given one or the other. And we can use that to help us determine if something's going to be acidic, basic, or neutral. Again, if the H plus concentration, which is the acidic part of the solution, is greater than the OH minus, which is the basic part, then again, it's going to be acidic. If they are equal to each other, we will then have a neutral situation. And if the OH minus is greater than the H plus, we will have a basic solution. We also obviously talked about the pH scale, which runs from 0 to 7 to 14. Less than 7 is going to be acidic. Greater than 7 going to be basic. And 7 there is going to be neutral. And remember, 7 sort of our midpoint there. As you go closer to 0, you become more acidic. And obviously, if you go the other way there, you're going to become more basic towards 14. We can calculate the pH. The pH, again, is equal to negative log of the H plus concentration. Remember, as we talked about with sort of the calculators you have for this class, you do need to work backwards there with the number first in a sort of non-display fashion. Hit the log button, then hit the negative button to do so. Remember, we also talked about a similar scale to pH, which obviously pH measures the H plus concentration in the solution. There is also the pOH, which measures the OH minus in the solution. And that's also a similar calculation, minus the log of the OH minus. Remember that the pOH scale actually runs opposite of the pH scale. So again, if you have a high pH, you will have a low pOH, and vice versa. If you have a low pH, you will have a high pOH. The nice relationship between those two is, again, the pH plus the pOH will equal 14. So it does give you a little bit of variety in terms of how you can solve for some of these problems. Again, if you're given the hydroxide concentration, you want the pH, you could actually calculate the pOH first and then just subtract 14 and you'll have the pH. You could also still use KW and convert the OH minus into the H plus concentration and then go into the pH. They both will give you the same answer. So again, a few different ways you can do that. We also talked about, thank you. We also talked about that if you have the pH given to you, from the pH, you could actually just get directly the H plus concentration from that. And again, the H plus concentration will equal the inverse log of the negative pH. And same idea if you have the pOH given to you, you could get directly from it the OH minus concentration. And that would be pretty much the same calculation, the inverse log of the negative pOH. Again, on this one, you do have to work backwards in your non-display calculator. So again, if you were going to, say, punch this one in to your calculator for your non-display calculator, you would start with the pH. You would then hit your negative button to make it negative. You then would hit your second button or shift button, and then you would hit your log, and that would get you to that calculation. Obviously, if you have a display calculator, if you happen to be using one of those, you go in this direction and punch it in. And with a display calculator, you would actually hit the second or shift button. You would then hit the log button. That would usually pop up a 10 and a caret. You would then hit the negative button, and then you would put the pH in. So again, the calculator you got for this class is a non-display calculator, so you'd be working usually backwards in these formulas. Same thing with obviously the pH calculation or the pOH calculation, same deal. Again, in a non-display for pH calculation, you would start with the number, so you would put your H plus concentration in there, making sure you use your exponent button. Then you would hit the log button. and then you would hit the negative button to make a positive. Again, in a display calculator, you would go straight across, just the way it's written. You would start with your negative, you would hit your log, and then you put your H plus concentration in using your exponent button for sure. All right, any questions on any of those things we talked about last time there, or how to punch those things in? All right, so I think we stopped at this example. I don't think we did this example, right? We did not do this example, I don't think. So why don't we do this example? Bless you. The pH of a solution is 3.14. What is the H plus concentration? Why don't we just add a couple other things just to practice one more time? What is the pOH? What's also the OH minus concentration? And is it acidic, basic, or neutral? Okay, so let's take a look. We have the pH here, and since we're added on and we're looking for everything, we do have a choice of sort of where we could go first. Obviously, with the pH, we could definitely get the H plus concentration right from it. We could also get the pOH from it as well. So I can go with the pOH first here. So the pOH will equal 14 minus the pH, which will basically be 14 minus 3.14 there. And that's going to get us here a pOH about 10.86, it looks like. Again, I could get the H plus concentration directly from the pH as well. Again, by taking the H plus concentration is equal to the inverse log of the negative pH. And once again, if you have a display calculator, it usually will pop up a 10 and a caret. On a non-display, it usually will not. And then you go negative 3.14. So once again, to punch that in on the non-display, you're going to start with the 3.14, make it negative, and then hit the second and log button. And you should end up with a number and like 7.2 times 10, 1, 2, 3, 4, negative 4. Remember, this does need a unit as it is a concentration in this case. Also, like we talked about here, our pH had two decimal places, so our concentration value will have two significant figures, again, kind of going backwards in that move. Remember, it is significant figures to decimal places, or decimal places to significant figures. It is not sig figs to sig figs on that sort of conversion. At this point, it does open up another option. We could use KW to get to our OH minus, or we can use the pOH value that we calculated to get to our OH minus. So again, here, it doesn't really matter which one you choose. I'll go with the pOH, and we'll do the same calculation there. The inverse log of the negative pOH. And again, that's basically something that looks like this, 1086 there. And looks like we'll end up with 1.4 times 10 to the minus 11 molar as our hydroxide concentration. And at this case, remember that when you're asked, is it acidic, basic, or neutral, there's just one answer. And that one answer should probably always be looked at the pH value, as that is the scale everybody has in their head. And that is definitely less than 7, which would make this acidic in this case. Any questions on that calculations there? All right, let's try one more here. We'll just do what the problem says. The pOH is 5.67. What is the hydroxide concentration here? Okay, so again here, when you're given the pOH, it tells you again what you can get directly from it, which is the OH minus concentration. And that's going to be that inverse log calculation of the negative pOH. Again, like, and punch that in there appropriately. Going to get us a 2.1 times 10, 1, 2, 3, 4, 5, 6, I think. If I counted that right. Hopefully. Yep. To the -6 molar in this particular case. Any questions on that there? All right, so obviously you need to be able to calculate pH, pOH, H plus concentrations, OH minus concentrations from given any piece of information. Yeah.
Questions are gonna want it, where are you gonna want it? And the other example you give us, the whole written out.
Are you talking about like the,
H equals, the 1 0 times, whatever. Like for the KW. So you have like examples like that, and then you have the other way.
right?
Are you gonna want it this way or the other way?
So you can depending on the question. So, for example, if you're asked to find the H plus concentration or the OH minus concentration, depending on the information given to you, you can solve it a couple different ways. You could do it either this way, for example, to get to the OH minus concentration. If you had like the H plus concentration, you can use KW as well. So there are a couple different ways that you can solve it depending on what you're at being asked for. So, for example, here, like yeah, like this particular problem here, you didn't have to use KW, but it's perfectly fine if you wanted to use KW, if that's your question. It's perfectly fine if you wanted to just like at this point get your H plus concentration, and then instead of doing what we did here, you definitely could have went back and did the KW calculation, and obviously should give you the exact same, pretty much answer, and that's perfectly fine as well. So either way is fine. Yeah. Okay. Other questions? All right. So up until this point, when we kind of talk about calculating the pH and everything like that, a lot of times what we're given is sort of just like a generic type of thing, like the H plus concentration is this, or the H3O plus concentration is this, or the hydroxide concentration is this. You may be given in some cases an actual formula of an acid or even a base and be asked to calculate the pH of it. So when we talk about the pH of a strong acid or really even a strong base, we can look at it and figure out sort of how to calculate the pH. And what helps us is that they are strong. And if you remember, speaking of strong acids, we had that sort of list of kind of 6 strong acids: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, hydroiodic acid. And, anybody lose keys? No? No. Thank you very much. Never. Thank you. Yeah. So this is our 6 strong acids. And remember, in terms of strong bases, those are a lot of times group 1 or group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide. Again, if you look at the periodic table and you go lithium, and then you kind of go down to sodium, potassium, make a right-hand turn to calcium, strontium, and barium. Any of these guys typically hooked up with hydroxide, like lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide. These guys are typically your strong bases. And because they're strong acids and strong bases, they are strong electrolytes. And if you remember, strong electrolytes are things that will 100% break apart into ions in solution. So how that's sort of beneficial for calculating the pH of a strong acid or a strong base, if you're given the actual formula, is, for example, if we take something like hydrochloric acid, and when hydrochloric acid is in solution, it is, because it is a strong electrolyte, going to 100% break apart into H plus and Cl minus. So again, in that solution of hydrochloric acid, you have none of the HCl units still together. You just have basically the ions floating around. And what's important for pH is negative log of the H plus concentration. So the amount of H plus floating around in that solution is really what's important to calculate the pH. And we could do that based on sort of hydrochloric acid's relationship between the HCl and the H plus. So in solution, this is really the most important guy. And when we look at the relationship between HCl and H plus in this case, it is a 1-to-1 relationship, which means that if you know the molarity of the HCl, because it is a 1-to-1 relationship, you basically would take 1 times that molarity, which basically will give you the same number. So whatever the concentration of this strong acid is, will actually be the H plus concentration. And you could go right into the pH equation at that point and calculate the pH of that hydrochloric acid solution. The good news is pretty much all of the strong acids, they are all monoprotic, which means they have one hydrogen, which means basically they are always going to be pretty much a 1-to-1 relationship, pretty much all of them. And that means if you know the concentration of the strong acid, that is basically going to be your H plus concentration, which means you could take it right into the pH equation and calculate the pH of that acid. Now, the same thing kind of works for a strong base. If you have something like sodium hydroxide in solution, because it is a strong base, it also will completely break apart into sodium ions and hydroxide ions. And same idea, if you kind of look at a beaker of that, you basically would have none of the NaOH units together. You would just have a bunch of ions floating around. And in this particular case, though, we don't have H plus, but just as important and helpful to us is we actually have OH minus. And we could actually figure out the OH minus concentration from our base. And by doing so, that will allow us not to calculate the pH, but will allow us to calculate the pOH. And that's very helpful because then obviously we could get to the pH by just subtracting 14 at that point, and that will get us to the pH. So with a strong base, they will also completely break apart, and you'll be able to figure out what is the hydroxide concentration and then go into your pOH and then subtract 14 to get to your pH. In this particular case, this is a 1-to-1 relationship between the base and the hydroxide. So if you know the molarity of this guy, it will be the same relationship. I will say that probably out of the two, the strong bases, especially strong bases from group 2 on the periodic table, will not always be a 1-to-1 relationship. So you may have to adjust the concentration. Any questions on that? So if we take a look at this example here, which I think was the experiment the other day, the first calculation, if we have 0.1 molar HCl and we wanted to know what is the pH, once again here, because this is going to break apart into H plus and Cl minus. If this is 0.1 molar, again, a 1-to-1 relationship means we take 1 times the molarity of the whole thing. And in this case, we will end up with 0.1 molar. That then can go into our pH minus the log of 0.1 molar. And that is going to get us a pH of 1, it should in this case. And I'll get us a 1.00 molar, in our pH in this case, 1.00. Any questions on that there? So if you're given a formula in this class of an acid or base, you could probably safely assume that it's going to be a strong acid or strong base, because to calculate the pH of a weak acid or a weak base, it is a much longer calculation than a strong acid or strong base. And you won't see that calculation until you take 1B. If you take 1B, you'll do that calculation. But for our purposes here, if you actually do see a formula, you could probably safely assume it's going to be a strong acid or base. So why don't you try that here for both of these? What is the pH of each of these solutions? We've got perchloric acid, and we've got a little calcium. First one here is perchloric acid. Again, that's on our list there of our 6 strong acids that we saw there, right here. So we know that this is going to be a strong electrolyte and going to completely break apart in solution, which means when we do have this basically in solution, it is not going to stay together. It will break apart into H plus and ClO4 minus perchlorate. And really, it is again the H plus concentration that we're interested in to calculate the pH. And we know that the concentration of the whole thing is 0.025 molar. Once again, as most of these strong acids are, it is a 1-to-1 relationship between the whole thing and its ions. That means the concentration of its ions, you would take 1 times the initial concentration. And that's going to leave us, obviously, here the same number. And that would be our H plus concentration. And now we could go into our pH equation minus the log of 0.025. That's going to get us here. Looks like a 1.60 on the pH here. On that one. Yeah. Correct. So it's like when we talked about with molarity in chapter 15, I think, our last chapter, how molarity works when it kind of relates to the ions is whatever it breaks apart into, the however the coefficient is, you just multiply the whole concentration by that coefficient, and that'll give you the concentration of the ion. Other questions? Speaking of that, here we have calcium hydroxide, which is a strong base. So when this breaks apart in solution, again, we're going to get a calcium ion. And in this particular case, we're actually going to get 2 hydroxide ions, similar to the question that was just asked there. It is the hydroxide here with the base that we're interested in. And since we do know that the whole concentration here of the whole thing is 0.025 molar, in this case, this is a 1-to-2 relationship. So to get the proper concentration of hydroxide in this case, you do have to multiply that concentration by 2, and this would be 2 times 0.025 molar. That's going to give us a hydroxide concentration in solution of 0.05 molar. And that is the proper hydroxide concentration that we'd want to use for our POH here. And I'll just go, I'll go up on top here. So our POH will be minus the log of 0.05. And that's going to get us here a 1.30. Remember, though, that that is the pH, POH. So the pH would be 14 minus the pH. So 14 minus the POH. 14 minus the POH, which would be 1.30. And that's going to get us here a pH of 12.70, which is definitely a basic pH, which would make sense in this case. So, like I said earlier, probably more so if you come across a strong base, you might have to adjust the concentration of the hydroxide, as again, most of the strong acids are monoprotic, so they're going to be a 1-to-1 relationship. But if you get into any strong base from group 2 on the periodic table, because group 2 has a +2 charge and hydroxide has a -1 charge, you're always going to get like a 2-for-1 deal on the hydroxide on that. So you'll have twice the amount of hydroxide in that. It'll be twice as concentrated. Questions on that there? The last thing we're going to talk about is, we'll talk about it, is a buffer. And a buffer is a solution that's able to resist changes in pH even when you add acid or base to it. So sometimes people, when they hear of a buffer, they think of it as something that is a neutral solution. And a buffer does not have to be a neutral solution. It could definitely be a neutral solution, but you could also have a buffer that's acidic and you could have a buffer that is basic. You could actually make a buffer at any pH you like. You could choose any pH you want and you can make an actual buffer solution. What it really is, as I mentioned a second ago, is it's a solution that has like a pH. And if you add acid or base to it, it will be able to maintain that pH without really big changes to the pH because you're adding acid or base to it. Will the pH change a little? It will change a little, but you will not get a really big jump or drop in the pH when you add like an acid or a base to a buffer solution if it's made correctly. So, for example, if your buffer was made at a pH of 4 and you added a little bit of acid to it, the pH after you added acid, maybe it's like 3.95 or something like that. It will stay right around 4-ish. It will not go from like a pH of 4 to like a pH of 1. You won't have this really big drop in it. It's able to resist those really big drops. Now, why is a buffer able to do that? It's actually what it's made out of, and you can make a buffer out of one of two combinations. You could either make a buffer out of a weak acid and the salt of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. So that's the deal with buffers. It cannot, and you cannot have a buffer. You cannot have a buffer out of a strong acid or strong base. So you cannot have a buffer that has either a strong acid or a strong base in it. And the reason why you need it to be a weak acid or a weak base, and by the way, the relationship between these two things is the Bronsted-Lowry definition. It is 1H plus difference between those two things. The acid conjugate base or the base and the conjugate acid is just 1H plus difference. The reason you need a weak acid or weak base is it will set up an equilibrium in that solution because it's a weak electrolyte. So if you remember, weak electrolytes mainly stay together, but they do break apart a little bit. So they're able to set up in the solution both a acid part, which I'll abbreviate as HA. They even throw arrows in the solution, not really, and a base part. So the buffer will have this, which is like the acid part of the buffer. And they will have this guy floating around in solution, which is the base part of the buffer. And that's really important for how a buffer is able to work is it has actually both of those things in the solution at the same time. And that's really crucial for its functioning. A strong acid or a strong base is a strong electrolyte, which means when they go into solution, it will completely break apart and you'll only have really like a base part. So for example, if you try to make a buffer out of HCl and sodium chloride, that's a strong acid and that is its conjugate base. Problem is when you put that into your beaker, because HCl is a strong acid, it's just going to break apart into H plus and Cl minus. This is a salt, which will break apart into Na plus and Cl minus. Now, floating around that solution, all you have is a conjugate base. You don't have any acid part of that solution to work as a buffer. So that's why this will not work. And why, if you take something like the most common buffer that everybody uses, which is acetic acid and sodium acetate, this is a weak acid. I know it's a weak acid because it's not one of those 6 strong acids that we talked about. This is its conjugate base. It's actually the salt of its conjugate base because there's a sodium ion in there. The actual buffer is between these two things. This guy and this guy is the actual buffer components. The sodium is just a spectator ions. It's just floating around. It's really not involved in any of the buffering part. And if you look at the difference between those two things, that is your Bronsted-Lowry difference. The only real difference is 1H plus. And when you do that and you put that into a beaker, the acetic acid, because it's a weak acid, will do that kind of weak electrolyte breaking apart into H plus and acetate. And once again, what you now have achieved in this case is you have again an acid part to your buffer, and you have this base part to your buffer as well. And again, that is, like I said, very, very crucial for how it works. So just to demonstrate how it actually works, let's demonstrate what happens when you put like an acid or base into something that's not a buffer. So if you took water, which is not a buffer, and you threw some hydrochloric acid into water, what's going to happen is, in this case, you're going to take your HCl, you're going to dump it in. It is, because it's a strong electrolyte, going to completely break apart into H plus and Cl minus. So 100% is what you're going to get on this side. And that means when you look at this solution that was water, you're just going to get this HCl breaking apart in it. And that's really bad, because what you just did is you just dumped in there a bunch of free H plus. So you have a bunch of free H plus. That means the concentration of H plus went up really quickly, and pH is related to the concentration of H plus. So because you just put a bunch of H plus in there really fast, you're going to see a giant drop in the pH. So maybe it'll go from like a pH of 7 down to a pH of 3 or 2, because you just influx into your water all this free H plus, and that's going to cause the pH to drop tremendously. And this is why water is not a buffer, because you got a really big jump in pH, right? Or actually drop in pH in this case. And if we take something like sodium hydroxide, which is a strong base, and do the same thing, and we add it to water, it will also break apart into sodium ion and a hydroxide ion. And same idea here, if we had water and we added this, because it's going to 100% break apart into these ions, you're now going to dump into this solution a bunch of sodium ions and a bunch of hydroxide ions that are freely floating. And that's also really problematic, because now what we just did, the water, is we dumped a bunch of hydroxide ions in there really quickly. That means we now have a lot of free hydroxide ions in the solution. That means the concentration of hydroxide will skyrocket. And if you remember, hydroxide and H plus are related to each other. So as one goes up, the other goes down. And what happens is you see a tremendous drop in the H plus concentration at this point. And what's going to happen is your pH is going to respond to all that hydroxide, and it's going to skyrocket upward, because now you got a lot of free OH minus in that solution. So you might see your pH go from a pH of 7 with the water to like a pH of 12 or something like that. A really big jump in pH, because you influxed into that solution a lot of free OH minuses. Any questions on that? So this is what happens in a non-buffer solution, and why you see a pretty big jump either downward or upwards in the pH, depending on what you're adding, when you don't have a buffer. But let's take a look at what happens when you do have a buffer. So if you added the exact same thing to, say, our acetic acid sodium acetate buffer, the difference is when you have the buffer here, you're going to get that acetic acid that's going to stay in solution. You're going to have some H plus, and you will have its conjugate base over there. It's acetate. So you'll have this guy and this guy in the solution. Once again, this is our acid part of the solution. That is our base part of our buffer. So now when you take that HCl and you dump it into this beaker that has this buffer in it, you're actually going to get a reaction that's going to occur. So you're now going to have an acid coming in that's going to react with the base part of the buffer, and you're going to get a double displacement reaction that's going to occur. I'll go down. And again, we're going to switch partners on our double displacement. You will make sodium acetate, and you will make some sodium chloride. Now, what happens in this case is you actually make part of the buffer, which is always what happens. When you react an acid or base with a buffer, you use part of the buffer up, and then you make the other part. So it's almost like self-regenerating part of it as you're reacting with it. And so that's definitely not going to screw up the pH because it's part of the buffer to begin with. We make sodium chloride, which is actually a neutral salt. It's not going to screw up the pH. It's actually what we don't see here that we did see with water. That's really the most important thing. What we actually don't see formed when we react this HCl with the buffer is we don't see any free H plus like we did with water. So because we don't see any free H plus, the concentration of H plus that was in that solution will remain relatively constant. So the concentration of H plus, because we're not forming any more, will remain relatively constant. And because of that, the pH will also stay relatively constant as well. And I say relatively constant because in reality, if you were following it with like a pH meter, you would see the pH go down a little bit, but it would not jump giantly. So this buffer would be something like 4.74 to start with, a pH. And if you add some acid to it, maybe it goes down to 4.68 or something like that, 4.6. It's not going to go from like 4.74 down to like a pH of 1. So you won't get this really big drop. You get a very, very small change in the pH because it's resisting change. So what happens in this case is when the HCl goes in, the H plus and Cl minus go in for a swim. But what happens is in this case, we do get a reaction with the H plus and the acetate part. So these guys come together to react and we'll make acetic acid. I wrote that wrong. That should be acetic acid on that side. I'm sorry. That should be acetic acid and sodium chloride to form acetic acid in this particular case. And it ties up basically that H plus that would normally be freely floating. So because the H plus gets tied up, keeps the H plus concentration constant and doesn't have a big jump in the pH. Same thing happens when you add sodium hydroxide to this buffer. It will react with the acetic acid over here. Try to do this right this time. There we go. And again, you'll get a double displacement where you will make sodium acetate. And in this case, some water you'll actually make. And when this goes in to our buffer, going to be a sodium and hydroxide sort of guy going in there. Again, we make part of the buffer, which again, it's always the case. So that's not going to screw up the pH. We make some water, which is not going to screw up the pH. But again, it's what we don't see. We don't see free OH minus being formed like we did when we looked at it with water. In water, we made a lot of free OH minus. Here we don't. And because of that, the OH minus concentration will stay relatively constant. And because the H plus is related to that, it also will stay relatively constant. And thus you will have a constant pH will stay relatively constant as well. Again, if you were following it, you would see the pH go up just slightly, but again, not a big jump in pH, just a very slight adjustment. So what happens in this particular case is the OH minus, when it comes in, grabs out the hydrogen and gets tied up in water, basically, and not freely floating in that solution. So how a buffer works to resist changes in pH is because it has an acid part and because it has a base part, when you add additional acid or additional base to it, it's able to prevent the formation of any free H plus in the solution when you add acid, any free OH minus in the solution when you add base. And because those H plus or OH minus concentrations stay constant, the pH is able to stay relatively constant and not like jump up and down. There is a limit to how good a buffer can work. You could actually blow through a buffer if you add too much acid or too much base, because what happens is when you have a buffer, you have again sort of your acid part and base part. So when you add additional acid, it will react with the base and you will make some more of the acid part of the buffer, but you will use up some of the base part of the buffer. And same thing happens this way when you add base to your buffer. It will react with the acid part, and you'll make some more of the base part of the buffer, and you'll use up some of the acid part of the buffer. And for example, if you just kept adding acid, you're just going to keep chewing up the base part until you no longer have any more of the base part of your buffer left. And if you continue to add acid at that point, you're now going to be dumping in H plus into that solution. And you're going to see a really big jump in the pH. This is actually what happens, for example, in that titration you did with the acetic acid. At the beginning of the titration, you actually make a buffer. And then because you keep adding base, you blow through your buffer. And that's what causes the big pH jump towards the equivalence point, and why, as some of you saw, right, your indicator changes color really quickly at that point, because there's a very big jump in pH. Because at the beginning of the titration, you had made a buffer, and so it's not changing pH a lot, but as soon as you keep adding your sodium hydroxide, you blow through it, and then you get this really big jump to the equivalence point, very big jump in the pH. And as we know, our indicators work off a pH range, and that's why we see a very big change in it. Any questions on that there? All right, that is chapter 16. And that is the last chapter on the last exam, which is Wednesday. Yes, that sounds right. I think Wednesday. And we're going to go off to the next chapter, I think. All right. So good news is final chapter of the season here, chapter 17, which is equilibrium. So we're going to talk about some parts of this chapter. We're not going to hit every part of it, I think. We're going to skip the last two sections, I think, of this chapter, as they're throwing it out of this class. So we'll just not talk about it too much at all. All right, so let's talk about equilibrium. And as we will talk about, equilibrium does actually involve a specific type of reaction. And these reactions are the ones where you actually see arrows heading in both directions. And when we talk about equilibrium type reactions, they are these type of deals. And again, we've seen these arrows with weak electrolytes. And this implies that this reaction is a reversible reaction. And basically what that means is there's two directions to this reaction. There is like the normal direction where we go from reactants to products heading in this direction. And that is sometimes referred to as the forward direction. What happens though in these type of reactions is after you make a certain amount of products, those products on the right-hand side will decide we want to kind of go back the other way. And they will start recombining with themselves, and they will head back in the other direction, which is going from products back to reactants. And that is what is referred to as the reverse direction. And this process will continue until it reaches chemical equilibrium. And as we'll talk about in this chapter, sometimes people, when they hear the word equilibrium, have a wrong indication about what it means. And it's probably because it sounds like equal in the name. So people think that when it reaches equilibrium, you have equal amounts of everybody on each side of the arrow. And that's actually not what it means. What it is actually referring to is the rate of the forward direction and the rate of the reverse direction will actually equal each other. So at some point, as our reactants are going to the products and the products decide to go backwards, back to the reactants, the rate at which the forward direction is going will equal the rate of the reverse direction. And that is what equilibrium means. Now, when that happens, what that essentially means is not necessarily we have equal amounts of everybody, What it means is once they reach equilibrium, everybody will be locked into place in terms of their concentrations or their pressures. So, whatever their concentrations were at the point when they reach equilibrium for A, B, C, and D, they are locked into those concentrations now. And that's because as quick as it goes to the right hand side to make products, they're just going to come back the other way just as quick. So it's going back and forth. So you're going to get a net no movement in a sense of anything happening on either side of the arrow in terms of this concentrations, because again, as quickly as it goes to the right, it's going to come back to the left. So if these guys locked in at equilibrium, and these guys' concentrations at equilibrium was like 2 molar, 1 molar, 3 molar, 2 molar, for example. What that means is they will be able to essentially maintain those concentrations indefinitely because of how fast is this going one way and coming back the other just as fast. Now, they will keep these concentrations exactly the way they are until you do something to screw up the equilibrium, which you can do. And we're going to talk about that later in this chapter as to what happens when you kind of mess up the equilibrium. But one of the interesting things about these type of reactions is you could actually screw up this equilibrium and it will actually self-adjust and it will self-correct itself, this reaction. It'll go, oh, you just kind of messed me up there. I need to get back to this equilibrium state. And what happens sometimes is it goes, well, to get back to this equilibrium state, I need to make more products. So we'll kind of make some more products for a time until it gets back to equilibrium. Or you may do something to it and go, no, 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 I need to actually make more reactants. And it will kind of go towards the reactant side and make more reactants until it reaches equilibrium again. And you could actually screw this reaction up and it will fix itself. Then you can screw it up again, it'll fix itself. And it's ever changing. You could like do something to it. Let's just say you wanted to get this reaction to go to the left. You could do something to it that will make it go to the left, and then it will reach equilibrium. Now you have maybe a little bit more reactants than you did products. And then you can go, I changed my mind. I actually want to send it back this way. And you could do something to that, and then it will push it back the other way. And you could kind of go back and forth many, many times. And it's always going to kind of self-correct itself to try to get to always this state, this equilibrium state where the forward reaction, the reverse reaction will equal each other. So there's kind of an interesting type of reactions that you can kind of mess it up multiple times and kind of push it one way or the other and just kind of move it wherever you kind of want it to go. So let's talk a little bit though about how reactions occurs and rates of reaction, since ultimately equilibrium is about the rate of that forward reaction to the rate of the reverse reaction, which by the way, rate is usually involves kinetics and how fast or slow something occurs. Now, when a reaction occurs, there's actually two things that has to happen for products to be made. Molecules has to hit each other, and they actually has to hit each other with the right sort of part of the molecule, sort of the active side of the molecule, and also has to have the right amount of energy for products to start to make. So these guys, when they come at each other, will hit each other. And if they have the right amount of energy, what that's going to initiate, as we can kind of see here in this picture, is it's going to initiate kind of the breaking of some bonds. And also, originally, if you look over here, there is no bond right there, but we're now going to start forming some bonds. And this is going to be this sort of partial making bonds and partial breaking bonds until finally we have all of our new products on this side with our new bond formation. Now, if you remember in our energy chapter, we talked about energy diagrams where we had like this hill that say the reactants has to climb to get to the other side. And we have this activation energy that we talked about way back there in chapter 10. And that is what is happening right here. So as this guy is climbing this hill to get to the other side, we're starting to break bonds, we're starting to make new bonds. And if you remember at the very top of the hill, that is the transition state we talked about. And that is what you have up there at the transition state. You have this sort of substance that has partially broken bonds, partially made bonds. And that's why it's at the very top of the hill of energy. It's a very unstable condition because they're all partially broken, partially made. They don't want to be in that case. And usually they will be able to drop down to the other side relatively quickly and get to our products in this case. So, as we talked about in chapter 10 about energy and energy diagrams, this is sort of what's happening in the process of a chemical reaction, as the only thing that we're doing is making bonds and breaking bonds in this case. Now, excuse me. How can we increase the rate of reaction or decrease the rate of reaction? There are several things that are really important in how fast a reaction takes place. And concentration is one of the important things. If you think about like a reaction taking place and things need to run into each other, if you increase the concentration of your reactants, so say you're A and B, and you have a lot of A and B floating around, or even just A, the likelihood of those guys coming in contact with each other now increases because they don't have to like float around looking for somebody. There's a bunch of it in there. They're going to run into them pretty quickly. And that's going to help initiate the reaction to take place. And that's going to speed up the rate of the reaction or how fast it takes place. Vice versa, by the way, if you have a really low concentration of reactants or even products, it's going to take longer in most cases for those guys to find each other, to react with one another. And that's usually going to slow down the rate of the reaction. Temperature also increases the rate of the reaction. If you increase the temperature, you typically will increase the rate of the reaction for kind of the same reasons. When you increase the temperature, you have a lot more energy involved and people are moving around a lot faster, which means if you had your A and B guys there and you increase the temperature, these guys are going to be moving around a lot faster, and there's probably a good chance they're going to run into each other a lot quicker than they would at a lower temperature where they're moving slower. In addition, when they do run into each other, because it's a higher temperature and because they're moving faster, they also will probably have the right amount of energy to get that reaction going because they have a little bit of extra energy sort of happening in that situation. So concentration plays a really big role, temperature as well. If you increase the temperature about 10 degrees Celsius, you typically, for a lot of reactions, can double how fast it happens. So you could increase the rate of that reaction by just increasing the temperature about 10 degrees Celsius. And that usually, for a lot of reactions, will double the rate of it. The opposite is true as well. If you threw everything on ice, you're going to have a lot less overall energy in that situation, and that's going to slow everybody down. Things are not going to have as much energy, and you're going to see probably a slower rate of reaction because it's going to take longer for people to come in contact with each other. When they do, they may not have the appropriate amount of energy to kind of kick that reaction off. And that is, again, this sort of energy diagram as we were talking about. We're starting to break those bonds as we come up the hill. We got this transition state complex where we have partially made bonds, partially broken bonds. And again, that usually will break apart into our products pretty quickly. Again, that activation energy is that minimum amount of energy that's needed for those reactants basically to turn into products or kind of make products. Remember as well that hill of activation energy also plays a really big role in terms of how fast or slow a reaction takes place. If it's a really big activation energy hill, it's going to take longer to get to the other side. Just like if you had a really big hill to climb to get to the other side, it's going to take you longer than if you had a smaller hill, right? And in addition, more people would probably be able to climb the smaller hill than the bigger hill. And it's the same idea here. In terms of reactants, there'll be a greater amount of reactants to get up and over that smaller activation energy hill than the larger one. So if your activation energy hill was like this, versus an activation energy hill like this. This is obviously a much bigger reaction hill to get to the other side than this one. And again, reactant molecules would be probably able to climb the other one a lot easier than the one on the right. By the way, this is a exothermic reaction where heat and energy is released, as our reactants are higher in energy than our products. This would be more of a endothermic reaction, as our reactants are lower in energy than products. That's why in an endothermic reaction, energy has to be put in to perhaps help people up and over the hill, right? To kind of need an overall input of energy to help people get over that bigger activation energy hill to get to the other side.